All right, here's a quick look at that function tangent stuff that I was talking about in class, just a little bit more in depth. I re-recorded this just to make it more current with what we were talking about when we were there. So the big things that you saw, just hold on to this idea that there's some misconceptions I want you to hang on to. I think you get the idea of a tangent. Great definition here to take a look at and remind yourself of. But if it passes through...
Thanks for the mechanical pencil.
You're welcome, buddy. Did it work out okay?
Mm-hmm.
Nice. Good. Got that homework ready to roll? I know we have all this technology, but we still need pencils, don't we?
Mm-hmm.
They come in handy. Did you finish all your work?
Yep. It
Awesome.
was just spelling.
That's pretty nice.
Proofreading.
Proofreading? Good skill to have.
It was easy.
Yeah, I have same thing. I have some homework stuff too, but thankfully I can do it all on here. Pretty easy to work with. Are you using what type of tablet are you?
Kindle.
Kindle. Fun. Kindle Fire. Cool. Yeah, we've had this iPad a while. My kids, somebody dropped it somewhere in there. One malfunction.
Where's your backpack?
I already finished my homework.
You already finished it? Can I see
He's
it?
working hard. He
Let me borrow.
He needed a pencil, and I happen to have one. Rarely does that happen, so.
Yeah.
Buddy, let's go check it and make sure you got it all done.
I got it.
Nice. Okay, so this piece is a misconception where you don't have it passing through. We think that it should not pass through the curve at any other time. Well, it can. Here it's just touching once, but only once, and passing through kind of as an intersection. That doesn't work. So just keep these in mind. These are not tangent lines here. Down at the bottom here in the lower right-hand corner, that's an important one. That actually works. That's a tangent line. It passes through the curve kind of more than once, but it's teetering at that moment. It's hard to get this. So we have misconception, misconception, misconception. This one kind of works, and I'll make more room and show you at the bottom. Cool. So now you can see tangent to must cross the curve only once, and that's an issue. But here, tangent line to a curve is a line that just grazes this curve at a point but does not cross the curve again. Well, this one is actually a tangent line. What it's showing here, it's grazing and it does cross again, so it's more than just that. So this one actually works, and this is good, efficient, proper tangent line. But here's the idea. The idea is that a tangent line teeters at a point and gives you a sense of how steep it is at that moment. And that's what our derivative that we figured out today was all about. It was a quick route to actually getting how steep that teetering line is. It's all about that local steepness at that very moment, that exact moment on that curve, rather than an average rate of change. It's one at that specific moment. And here in these examples, what I want to show you is let's get a graph going for these. I'm going to get a nice pen color going, black for my grid. Let's go like this. So negative 2x, if I graph that, that's a slope of, remember, that's a slope of negative 2. And what's interesting about that is that I'm going to graph this line, negative 2x, it goes through 0 because the y-intercept is 0. And then it asks you, hey, find the tangent line to that particular graph at x equals negative 1. So here's negative 1 on the x-axis. If I go to that curve and put a tangent line up against this, I hope you're wondering how I'm going to get a tangent line to touch only once, because you can't get a line to touch only once on another line. So the issue is a line tangent to another line actually ends up being the same line. They're up against each other. It means that the slope anywhere on that particular line, that negative 2x line, is always negative 2. So lines have a constant slope. The tangent is always the same steepness. You go over to the next one here on the other side. Let's make a quick graph out of that for you. Here, I can make this better. Let's make straight lines. It'll be fun that way. All right, there's my nice little grid. Now, the negative, 1 minus negative x squared is an upside down parabola through 1. So it's really roughly drawn. And at x equals 0, I'm supposed to find the tangent line. Well, the tangent line there, check this out, is exactly 0 at that moment. So, and I'm sorry that I didn't draw the scale, but right at x equals 0, which is at that kind of the peak there where it hits at 1, the height of 1, the slope of that tangent line is horizontal. Remember, that's 0 fun. You put that little slope dude hanging out on there. I wonder if I could draw a decent slope dude, just for fun. There he is, and he's got his bald little head. There he is, skiing across there. 0 fun, poling all the way. I hate poling. So then we get down to the next function here. Bam, bam. That's a nice looking cubic function. At x equals 1, you're supposed to actually graph this, oops, sorry about that, in a reasonable window. Man, why can I not get this right? If I take and graph a nice, decent cubic that looks like that, at x equals 1, you're trying to find out what the tangent to that curve is, and you're trying to find out, is it one of these, or is it facing down? Well, quickly you decide as you graph these and try and get tangent lines. It gets pretty hard to do it by hand. I can go over to the next one. It's a chordic function. It's upside down. It looks like that. What really becomes achingly apparent is that this derivative thing we learned is super handy. So let me take a second, do some derivatives, and show you how handy it is to find the slope of the tangent in that route, and then just confirm it against the graph and see that you're doing the right thing. All right, let me show you a little something with this stuff we did today. I want you to focus on that function over there, number 3. F of x equals x cubed minus 3x squared plus 3x minus 1. Take that x cubed out front. We took the derivative of that today, 3x squared. Well, if I isolate each one of these little terms here and just do the derivatives separately from the rules that we learned today, even that negative 3x squared right here, the derivative of that is actually negative. You remember, you multiply the power, bring the 2 down, multiply those together, get negative 6, and then x to the first. Okay, and then I go to the next term. Now 3x to the first, we didn't get to that in class, but actually the derivative of that is 3, because 1 from the x to the first comes out front. 1 times 3 is 3. X to the, now if I take it down by 1, it becomes x to the 0. And then we'll find out that actually ends up being just plain old 3. And then minus 1 here at the end, the derivative of that is 0. Now I'm going to go on the next little snippet here and show you where that comes from. But I want you to know that power rule that we applied in class, you can actually reapply it in a polynomial with multiple terms. So I just did it actually 4 times, and I get the derivative even of more complex functions. So I can get the slope of the tangent anywhere on there too. At x equals 1, we can do it. So I'm actually going to get to that here before long. We can do the same here with the next one. So if I go, let's go green this time, x squared. If I take the derivative of that, that's 2x, and the derivative of negative x to the 4th, if I bring the 4 out front, is negative 4x cubed. So those are the derivatives respective to those particular functions. And we can actually just put in these values of x right into the derivative to find the slope at that point. I can do the value of this one here in blue, and I can put that into my derivative and get the slope there as well. I'm not going to do it, but the idea is that you can graph the tangent and try and estimate it by hand, or you can use the cool techniques today that we found out and find out how steep it is directly. Hope you enjoyed that. I have some problems that you can check in on that worksheet, try and graph those and put the tangent against it. And if you would, the next thing I'll do is I'll actually get the derivative going on how to do polynomials, derivatives of these longer things, and use them to answer what the slope of the tangent is on each of these functions.